Okay. So let's begin. So to remember where we are, last class we derived this multiplicative weights mechanism, which solved, in some sense, a pretty simple problem, but it solved it pretty well. Okay, so just to sort of remember what is the simple problem that multiplicative weights solved. We had k actions we could take. Every day we had to decide which of these k actions to take. And we'd get some payoffs or costs that could be totally arbitrary. And the algorithm would experience the cost of the action it took. And what we were able to promise was that if we looked at the difference between the cost of the sequence of actions the algorithm took and the cost of the best of these fixed k actions in hindsight, okay, like so a simple benchmark class, best fixed action, but with the benefit of hindsight, that our algorithm was able to do pretty well compared to this benchmark class. That as we ran this interaction for t time steps, this gap would grow at a rate that was only like log of k times square root of t. Okay, so it grew sublinearly with t, but like maybe even more impressively, the penalty we sort of paid for having a large benchmark class, it grew only with the log of the number of policies, right? And if you think about this, this is pretty good. We sort of described our benchmarks as being fixed actions in hindsight, but there was nothing about the algorithm that required that those be the benchmarks, right? Like if you wanted, the benchmarks could have been more complicated things. The benchmarks could have been actions that corresponded to policies that said, well, look at your history, apply some machine learning algorithm, some predictive algorithm that predicts which of the sort of atomic actions you should take next. And we could have incorporated those as our actions as well, right? Like we could have competed with any set of k benchmark policies with regret that scaled only logarithmically with k, which means that it's very cheap, at least information theoretically, in terms of this regret bound, to compete with a very big class, right? Like log k grows slowly, right? So if we have some parameter d that we think is sort of reasonable to run in, reasonable time to run in, we can sort of compete with 2 to the d policies, at least in principle. But sort of maybe the substantial caveat is that although the regret bound grows in this extremely mild way with the number of benchmarks we're competing against, the running time of the algorithm does not. Right, the running time of the algorithm. That George. Yeah, happens to the best of us. Right, so the running time scales linearly with k. Okay, so maybe just to sort of have a concrete example in mind as we sort of go through this lecture and think about what we can do about this problem, let's think about what is called the online shortest paths problem. Okay, so suppose we have a road network, say, like the set of all roads in the greater Philadelphia area, which maybe we represent as a graph. Okay, so like road segments are edges in this graph. Okay, and suppose we would like to drive from some starting location to some ending location, maybe every day. Okay, so maybe like, maybe I live here. Here's my house. I work here. Here's my office. It's like the Comcast Center or something. And every day, what I need to do is I need to pick a path through this graph for my commute. It starts at my house and ends at my office. Okay, and I do this every single day. Okay, so it's sort of one of these sort of repeated interaction settings that these expert algorithms are good at, right? Like what we'd sort of like to do is to every day decide a path to use to drive to work, so that my commute time, which is maybe the thing I'd like to minimize, is no worse than if, with the benefit of hindsight, I had sort of planned out the best fixed path that minimized traffic. Okay, so how should I think about traffic? Well, maybe one way to think about it is that sort of the cost that I experience on sort of each leg of my trip is sort of a function only of what's happening locally on that road. Okay, like if I'm thinking, you know, how long it takes me to drive from, you know, this along this initial segment, if I'm taking like this path to work, you know, I don't care what the traffic is on these other parts of the road network. On this initial segment, what I care about is what's the congestion here. So maybe like a not terrible way to model my cost in this setting is that really there's a cost for each road, like the congestion on that road when I take it. And my total cost is the sum of the costs of the roads on the network that I take. Okay, like I have to drive along all of these road network, all of these sort of individual road segments to get from my home to my office. My commute time is the sum of my commute time on each of these roads. Okay, so this is some interaction, but because of the combinatorial structure of graphs, it's like an interaction that potentially has a very large number of options. Okay, so let's suppose that you know, in this graph, maybe there's like D edges. Okay, like D for Philadelphia might be something big but manageable, right? Like it's something that, you know, maybe I can't like, you know, remember all of the roads in Philadelphia, but they fit into the, you know, working memory of my GPS device. Okay, but the set of paths that I have between S and T, that could be like truly enormous. Like the set of paths in a graph with D edges could be on the order of 2 to the D. Right, and you can write down road networks for which the number of paths really does scale exponentially with the number of edges. Okay, so it might be that, you know, although it's feasible, maybe it's not feasible for me to remember all the roads in Philadelphia, but, you know, it's feasible for my phone to do it. It might really be that it's infeasible to sort of maintain any kind of state over all of the possible paths in the graph. That's like exponentially large. Now, if you look at what multiplicative weights can guarantee us, you know, if you don't worry about running time, actually, it's not so much of a problem, because we got this truly remarkable regret bound that sort of depended only logarithmically on the number of actions. Right, so in this interaction where what I do every day is choose a path, the number of actions I have available is exponentially large. It's 2 to the D. But, you know, at least if I, you know, scale everything appropriately so that the payoffs are, you know, in a fixed range, you know, the regret bound that we get out of multiplicative weights, you know, it's just on the order of D times T, right? Because log of 2 to the D is only D. Okay, so like multiplicative weights actually gives us like a decent regret bound, even when the action space is enormous. The problem is not the regret bound. The problem is we would be hard pressed to try to run multiplicative weights, because what is multiplicative weights doing? It has to explicitly maintain a weight for every possible action. And here, there's an astronomical number of actions, right? A combinatorially large set of actions. We just can't maintain those weights. Okay, so information theoretically, multiplicative weights actually gives us a pretty good way of playing in an interaction like this. But computationally, it would be extremely difficult to implement. that make sense? This is maybe like a motivating scenario for this class. We're going to solve, and what we're going to do this class is we're going to give an efficient algorithm that's going to get regret bounds like this, but can be run, efficiently in time polynomial in D, not polynomial in 2 to the D, for a class of problems that includes this thing along with a bunch of other stuff. Okay, does that make sense? Questions about the motivation before we go on and sort of talk about this class of problems, sort of both why we might have a setting where there's really a lot of actions, why multiplicative weights, if you just look at its regret guarantee, actually gives, a pretty attractive bound, sort of because it had this amazing logarithmic dependence on the number of comparators, but also why we can't run multiplicative weights, because multiplicative weights is sort of explicitly every day enumerating all of the actions and also maintaining memory state that is like linear in the number of actions. Does that make sense? Okay. So, yeah.
So, kind of similar to like so can you do the same thing? You just take a random sample of products and then just find out like family relations, and then you put another random sample.
Yeah, that's tricky because here the problem, I mean, there's sort of two problems. One, which is sort of related to sort of estimating the gradient. What's the gradient here? We'll make this more explicit when we cast everything we've been doing as like online convex optimization. But like the cost vector, the vector of costs assigned to each action literally is like the gradient of our optimization objective. And it's true that in this case, it has a dimension equal to the number of actions. We can't like write it down, but we're going to assume, the fact that we have this sort of like additive structure where the costs decompose across the edges, that is giving us an efficient representation of the gradient. That's going to be important. But that's not the only problem, right? Even when we can represent the gradient efficiently, this vector of costs, the problem is just sort of this representational issue. Like what these no regret algorithms are doing is they're maintaining a probability distribution over the actions. And multiplicative weights is explicitly maintaining this probability distribution as like a vector of length equal to the number of actions. And that's sort of the more difficult problem to solve. Like, not how do you estimate the gradients, where in this setting, the gradients have a concise representation. It's sort of like computationally, how are you even representing every day your, the distribution that you're playing?
I mean, like, almost 1,000 and just like within those, then at the end of each like and try to think like the best one and then do example another one.
Yeah, you could try stuff like that, but you sort of like it wouldn't work for a couple of reasons. But first of all, like, the best path in hindsight might, like random paths they're going to concentrate, that they're going to look all sort of similar. Like the best path in hindsight might not be typical. So at least you would need some like clever sampling strategy. But sort of maybe the more important obstacle is like this thing of keeping around the best ones. That might make sense in a setting where there's a distribution, where the history is somehow predictive of the future. But we're going to want algorithms that work sort of in the worst case. And you might then worry that it is exactly those paths that look bad, bad in the past that you've discarded that are the ones you needed to keep around.
Well, you can sample it.
Yeah, I mean, you can imagine trying to derive algorithms in that way. And if, like that would be it would be cool if you could do it, like, and, we have a class project. So, like, I'd love to see the write-up. I don't know how to solve the problem in that way. For this particular version of the problem, there are ways to design, there is structure to paths that would let you design sort of bespoke algorithms that would sort of, for this particular version of the problem, it turns out you can sort of come up with some implicit representation for the weights that multiplicative weights would have come up with. But we're going to solve a more general version of the problem. Yeah, you're describing like, you know.
I was just trying to look at that.
Yeah, but I think the analogy is, yeah, so the gradients here are the cost vectors. The challenge we're going to need to solve is not how to compute the cost vectors, because we'll see, you know, in this problem and in the more general version, I'm going to write down the cost vectors are going to have this sort of low dimensional structure, which are going to help us in representing the cost vectors. So unlike in sort of full gradient descent, the difficult thing here is not the computational task of computing the gradient. That we have access to. The difficult thing is the internal representation that the algorithm has for the distribution it's going to play each round. Okay, good question. Other questions? Okay. So the general version of the problem we're going to solve is called online linear optimization. Okay, and it looks like this. So the learner has some action space that we can represent or embed as a subset of d-dimensional space. So we can represent each action as a d-dimensional vector. Okay, maybe just sort of using online shortest paths as our running example, what would be the vector representation of a path? Well, d here would be the number of edges in the graph. And the way we would represent a path is as a d-dimensional vector that contained a 1 in every coordinate corresponding to an edge that was included in our path, and a 0 everywhere else. So we would view a path as a subset of the edges, particular subset that has path structure, and the vector representation of the path would be the indicator vector, the d-dimensional indicator vector telling us which edges are in the set and which are not. Okay, so you know, not every, right? So crucially, not everything in not every d-dimensional vector is a feasible action. Like in the online shortest paths problem, most of them are not. Only indicator vectors of sets corresponding to paths in the graph that have this particular combinatorial structure are feasible actions. Okay, so the action space can be embedded in R to the D, but it is not all of R to the D. Okay. The adversary has action space I'll call C, and that's also a subset of R to the D. Okay, so in the online shortest paths problem, what the adversary does is basically they assign some congestion to every road in the road network. Okay, but again, it doesn't have to be all of R to the D. There could be some structure on this. For example, you know, it may be the congestion has to satisfy flow constraints or something. Maybe, you know, if we've got a lot of traffic on 2 one-way roads going into, you know, a third road, that third road's also going to have a lot of traffic. Okay, so these, both of these can be sort of structured combinatorial sets. Okay, and then we have an interaction that sort of looks a lot like the experts interaction, just in this high dimensional space. So at each round T, the learner chooses an action AT, which is actually a probability distribution over their action space. So just like in the experts problem, they're allowed to randomize. Okay, so the thing the learner chooses in the online shortest paths problem at this moment could be a distribution over paths. And that's going to be important if you want regret bounds against an adversary, because if your algorithm is committing deterministically to one path, what the adversary could do to mess up your regret bound is make sure that on that day, that path is heavily congested and nothing else is. Okay, so the only kinds of algorithms that could possibly have regret bounds of the sort we talk about against adversaries must use randomization, and the learner will indeed use randomization. The adversary then chooses a cost vector in C, and the learner experiences cost CTL, which is the inner product between their action and the cost vector. Okay, so this is the linear part of online linear optimization. Okay, so again, going back to the online shortest paths problem, right, like this linear structure is important. In general, it's sort of too much to hope for that you could have k arbitrary actions and be able to get no regret amongst them in sort of running time that scales only logarithmically with k. Because if the rewards or the costs of these actions aren't related in any way, there's sort of no way you can avoid explicitly representing these cost vectors, right? I can't like sort of ignore coordinates if I know nothing about them. The online shortest paths problem, however, even though it has this enormous action space, the costs have this low dimensional structure, right? Like, even though I have sort of 2 to the d paths through a d edge network, if you tell me what is the congestion on each of the d edges, just d numbers, that's enough for me to compute for myself what the cost is for each of the 2 to the d actions. And what do? I just sum up the costs along the path that I took. And what is that? Well, if I represent a path just as the indicator vector of the edges contained within that path, the cost of the path summing up the edges is no more than the inner product between the indicator vector representing my path and the vector representing all of the costs in the network, 1 for each edge. Okay, so that's the structure we're going to take advantage of. And that's the only structure we're going to take advantage of. We're not using any other, like we're going to solve online linear optimization in general. It can represent online shortest paths if A is the set of indicator vectors for paths in a network, but that's not important to what we're going to prove. The thing that is important is the fact that the costs for each action can be represented as linear functions in some lower dimensional space. Okay, does that make sense? Questions about the model? Yeah. It is kind of bad notation, yeah. So like, more generally, I guess, what is this notation? So A is some action space. It's some R to the D. It's some subset of R to the D. Delta of A is the convex hull of that space. So, in general, the way I've defined it, it's possible that A is already convex, in which case delta of A is just A. If A is already convex, you don't need to randomize. More generally, if I think of A as representing distinct actions, then I can always view the convex hull of A as probability distributions over those actions. But as vector, but I can represent those vectors also, those objects are also vectors in R to the D. They're just they're just some convex combination of the discrete things, right? So if you don't want to think about probability distributions, what we're doing every day is we're selecting elements in the convex hull of our action space. Those are just the things that live in this space are just vectors. So it makes sense to talk about inner products, but a natural interpretation of that when I have discrete actions is that these are probability distributions over the actions. So it's, maybe like sort of confusing, but it is not wrong to talk about the inner product of these things. Yeah, good. Other questions? Yeah.
Is there any, I guess, if any is like a subset of convex hull,
So these are going to be, in principle, continuous probability distributions.
So if it's continuous, no one has density. Then is it on the same? Cost assigned each was cost.
Its costs. So in this case, the costs, like if we think of online shortest paths as an exemplar, the costs are assigned to the edges. Okay, so what are what are the elements of A? They're indicator vectors corresponding to paths. What are the elements of the convex hull of A? These things that we're taking inner products with. They are sort of, they have real valued weights in each coordinate corresponding to the probability that you take that edge if you sample a path from this probability distribution. So there are vectors that are in the convex hull of indicator vectors of paths.
So C has a constraint where they have. You can't change the cost of each vector from which.
Well, C is just a vector of length equal to the number of edges. So C is just a d-dimensional vector. So it has a, so in the online shortest path encoding, a coordinate corresponds to an edge. C just has a cost for that edge. Make sense? Okay. Yeah. Oh no, in general, it shouldn't be clear how to do this. So we're going to need the rest of the lecture to figure out how to solve this problem. So like the goal of this lecture is going to be to give an efficient algorithm that can solve this problem. But yeah, multiplicative weight solves this problem in an inefficient way. It's sort of explicitly representing this distribution as a vector of length 2 to the d. And the entire challenge here is to try to do that more efficiently. Does that make sense? Good. Other questions? Okay. Yeah, so maybe that question about computational efficiency is a good one to sort of lead off with, what can we even hope for here? So, you can encode the online shortest paths problem like this, but you can also encode like the online Hamiltonian path problem here, right? Like maybe every day my goal is to pick a Hamiltonian path, a circuit that visits every vertex once, and I want to pick the one that minimizes cost. Okay, and I want to do the one, I want to have no regret to the best fixed Hamiltonian path in hindsight. I can encode that just as well in a d-dimensional online linear optimization problem. But the Hamiltonian path problem is NP hard. That is, even if I just have a fixed instance, even if I just have a fixed cost vector, we don't have efficient algorithms to solve the problem, right? Computationally efficient algorithms. So like the online problem, the sequential problem is only harder computationally than the fixed problem, because it could be that the adversary just has a fixed problem in mind and gives me the same cost vector every single day. And then the only way I can get no regret is to solve this fixed problem. Okay, so because of the generality in which we have defined the online linear optimization problem, a first observation is that it's too much to hope for to ask for algorithms that efficiently solve this problem in every case, just because I've defined it so generally that it encodes problems that even in the easier static setting are NP hard, right? The shortest paths problem is something that in the static setting we can easily solve with Dijkstra's algorithm. So maybe it's not crazy to hope to solve it in the online setting, but the online setting is strictly harder than the static setting because it includes the static setting as a special case. So we can never hope to get efficient algorithms in the online setting that we can't get in the static setting. So the best we can possibly hope for is to get online algorithms, efficient online algorithms, whenever we have efficient static algorithms. Okay, or in other words, the best we can possibly hope for algorithmically is to reduce the computational problem that we need to solve here in the sequential setting to the computational problem that we need to solve in the static setting. Okay? So that's what we're going to do. We're going to assume that we can solve static optimization problems over this set A. Okay, so in particular, what we're going to assume is that for any vector of costs, we can find the action, which I'll call A star of C, that minimizes amongst all of the vectors in A, the inner product of A and C. Okay, like this is the thing. This is, if we add up all the costs in hindsight after T rounds, our hope is to do as well as the fixed action that minimizes the inner product with these aggregate costs. So we're sort of out of luck if we can't even compute that thing. Okay, in the online shortest paths problem, we can do that. In the online shortest paths problem, this batch, this offline problem just corresponds to being given a vector of costs along each of the roads and finding the shortest path. That's Dijkstra's algorithm. In the online Hamiltonian paths problem, that would correspond to finding a Hamiltonian path in a graph. That's an NP complete problem. Okay. The approach that we're going to take to circumvent what would otherwise be this difficulty is we're going to give what is an algorithmic reduction from the online sequential optimization problem to the online static optimization problem. If we can solve, what we're going to show is, if we can solve this problem, the static problem, then we can solve this problem with a good regret bound. Yeah. Mm-hmm. Yeah, so let's see. One can consider that kind of problem. And the story gets complicated and interesting. I don't think we're going to do it in this class, but yeah, shortly I'm going to maybe put up on the website like just a whole bunch of papers on different topics for you guys to consider for your project. That is a line of research. So what we're doing now is we're reducing the problem of online sort of linear optimization to the problem of exact offline optimization. You can also ask, what if I have an offline approximation algorithm? When does that give me some approximation to the online problem? The answer is sometimes, but not always. It depends on the structure of the approximation. That's a good question. Not gonna say much about it in this course, but there's, yeah, you're pointing towards a whole line of work. Good. But for now, we're gonna sort of divide the world into problems we can solve exactly, efficiently, and problems we can't, and not worry ourselves about approximation. Yeah. That's right. I am going to use the fact that I'm able to optimize for C that fall outside of this set as well. And it's an interesting question when you need that and when you don't. Another good question. Other questions? Okay. All right, so like, how can we use an oracle like this? How can we use the ability to solve these batch optimization problems? So let's, maybe like go through a first attempt. Yeah.
So that's is not just average thing along.
Excellent question. Yeah, that's exactly what I'm gonna. That's what's going to be our first attempt. So far, I just have assumed that we have the ability to solve problems like this, to optimize over A, the inner product with some C, any C. The question we need to ask ourselves now is, how is this useful? What C should, what C should we be feeding to this thing? And a very natural, right, like what we're trying to do is compete with at the end, the best fixed action, the inner product with the best fixed action with the average of the C's we've seen so far. That's the that's the average cost of the best fixed action in hindsight. And so an extremely natural thing you might try to do is to just every day optimize according to the average of what you've seen so far. Okay, that's called follow the leader. Okay, so what are we going to do? Very simple algorithm in rounds. We're going to compute the average, or just so that we don't have to carry around, fractions, just the sum of the cost vectors that we've seen so far. So the sum from day 1 all the way up through yesterday, day t-1, all of the cost vectors we've seen so far of the cost. Okay, this is just the cumulative cost seen so far, but we could divide by t-1, it would be the average. And we'll just select the action AT, which minimizes amongst all of our feasible actions the inner product with the vector of costs we've seen so far. Okay, natural thing to do, because if play stopped today, or if it stopped yesterday, this would be the benchmark we were evaluated against. This is the payoff of the best action in hindsight through yesterday. So if that's sort of the running target, if that's the thing we're going to be evaluated against, like maybe it's a good idea to just play that every day. Okay, that's why is it called follow the leader? If we're keeping track of the cumulative cost of each action so far, this is the action that has lowest cumulative cost. It is the leader so far. Okay, so what do we think? Is this going to be a promising algorithm? It does reduce to online linear. It does reduce to batch optimization, right? Like we're calling this optimization algorithm at every round. Yeah. So what do we think? Like, we just analyze this. Does it have a good regret bound? And if not, what's an example that might demonstrate why not? Even if you've seen it before, I know many of you have seen follow the leader before. It's a rhetorical device to keep the class moving, so don't. Yes, Natalie.
Every single round, one thing that's slightly better than the other thing, but then that round the law is actually the other direction.
Yeah, like the problem is like here we're making really sharp distinctions, right? Like, we're keeping track basically. What is this doing implicitly? By the way, like this is already a way to think about how we can use this optimization oracle to implicitly implement algorithms that would be hard to do explicitly. What is the algorithm that this is implicitly implementing? Well, implicitly, what this is doing is it's keeping track of the loss of each of the 2 to the d actions, the loss of each path, and playing the one that has lowest cumulative loss so far. Except it's not doing it by explicitly keeping these things around. It's just keeping around the sum of the costs, which turns out to be a low-dimensional sufficient statistic, and computing the best response, the leading action on the fly. Okay, so we're so first of all, we're already like implicitly implementing a strategy that naively would have kept around states equal to the number of actions. But what are we doing? We're sort of making these very sharp distinctions. The costs for 2 actions might be extremely close, but like based on whether one of them has slightly better cumulative cost in hindsight than the other, we are sort of, rapidly like, swinging the steering wheel one way or the other to choose one of them versus the other. We're making these hard distinctions. So this is the kind of thing that can go wrong. So let's suppose that what we're doing is we're really just encoding like the 2 expert problem here. Okay, so there's really 2 actions we can take, like left or right. Okay, how would we encode that as an online linear optimization problem? Well, just as, just with the 2 indicator vectors, which says, choose the left action or choose the right action. Okay, if this is our action space, It's just encoding like the two experts problem. We've got two actions. And then what if the costs end up looking like this? The first one, just to sort of break symmetry, is 1/2 0. The first action has cost 1/2. The second action has cost 0. Then the second cost vector is 0, 1. The first action has no cost. The second action has cost 1. The third cost vector is 1, 0. The fourth cost vector is 0, 1, and so on. Okay, so every day the cost just alternates between, like you get slapped on the wrist if you play the left action, or you get slapped on the wrist if you play the right action. Okay, right. So it's alternating, like left wrist, right wrist, left wrist, right wrist. Each fixed action is not that bad. I mean, like if I always select left, I get slapped on the wrist half the days. If I always select right, I get slapped on the wrist half the days. But what's going to happen if I play follow the leader? All right, well, who knows what I do on the first day? There's no history, so I could choose either one. But on the second day, the first action has positive cost, the second doesn't. So I choose right, and I get slapped on the wrist. The third day, the first action has higher cost than the second action. It has cumulative cost 1 versus 1/2. So I choose left, and I get slapped on the wrist. The fourth day, things have reversed. The right has lower cumulative cost. I choose right, I get slapped on the wrist. Okay, and so if I end up playing follow the leader, I choose exactly the wrong action every day. Okay, so I have cost growing linearly with t, whereas the best action in hindsight has cost, I have cost t basically, whereas the best action in hindsight has cost t over 2. And so my regret grows linearly with t. My regret is t over 2. It does not satisfy these nice sort of sublinear bounds that we're aiming for. Okay, so follow the leader doesn't work. Right, basically because it can exhibit this sort of oscillatory behavior that chooses the wrong action every single day. Right, like, yeah. Well, follow the leader is making a deterministic selection every day. Right.
Like when you're for your benchmark, you have to choose either left or right.
The benchmark, you have the benefit of hindsight with the benchmark.
Right.
So the benchmark is the better of the two. In this case, it doesn't matter because both of them have cost t over 2 in hindsight.
Right. So what's wrong?
No, the benchmark's good. The algorithm's bad. Like the algorithm does much worse than the benchmark.
But follow the leader is for the benchmark, right? For that, I thought the purpose of
Oh no, the benchmark is still the cost of the best fixed action in hindsight. Like an online shortest path, if I just always stick to the same route, like for the best route in hindsight, what's my average commute time? The algorithm is going to play adaptively somehow. It's going to choose a different action every day, and we want to make sure we don't do worse than the benchmark, the best fixed action. This is an algorithm that is making an adaptive choice. It's choosing what to do every day. And it's making, in this case, bad adaptive choices. It's doing substantially worse than the benchmark. And so if we want to design an algorithm that makes good adaptive choices as measured with the benchmark, it can't be this algorithm. Good. Other questions? Okay, and like intuitively, right, like if we look at the average cost in hindsight to these actions, they become almost exactly the same, right? Like the average cost in hindsight is sort of like, 1/2 and 1/2 plus 1 over t, something like that on this sequence, right? So the difference between the cost in hindsight of these two actions is like going to 0. It's like, the difference is only, whether we've played like an odd or an even day, that like they're off by 1 in absolute terms, and in average terms, they go to 0 at a rate of 1 over t. And yet, like what the algorithm is doing is it is making big swings in its behavior every day as a function of what are these sort of diminishing differences in average cost. And that's kind of the only problem. Okay, like somehow, if we can avoid examples like this, then we'll be okay.
The action is not randomized.
That is also a problem. I mean, that is a more general problem than this problem. Yeah, so that's a good observation. So we could come up with exactly the same example, not just for this algorithm, but for absolutely any algorithm that makes deterministic predictions. The sequence of costs wouldn't necessarily look like this, but the adversary could generate the sequence of costs by saying, look, the adversary knows the history. The deterministic algorithm, the adversary knows which action the algorithm is going to play. The cost vector chosen by the adversary is going to put cost 1 on the action chosen by whatever deterministic algorithm you're using, 0 elsewhere. The cost of your algorithm will be t. The cost of the best action in hindsight will be 1 over k. Yeah. Yeah, but it's important. Like what we're seeing is if what you're doing is choosing a distribution that is actually a point mass on a single action, then the adversary can always screw you over in exactly this way.
Yeah, but he doesn't screw you over by deferring.
That's right. So yeah, because the adversary knows everything in the past, basically.
Sorry, that's if you choose a cut mass, it doesn't matter.
Oh yeah. So the two things are equivalent. So like if the adversary knows your algorithm, then he knows what distribution you're going to choose every day. But yes, yeah, the adversary just observes it in the way we've written it down. And so it had better be that the thing that he observes is a distribution, not a point mass. It's like if I were playing rock, paper, scissors with you and told you that I was going to play like rock today. Good old rock. Okay, good. Other questions? Okay. So here's the fix. We're gonna just tweak this algorithm a little bit, basically with the intuition that we're going to try to do something that's going to break this bad example. And we're going to find that this bad example was basically the only obstruction. If we break that bad example, we're actually going to get a good algorithm. Right, so what was the problem? It was sort of this hard tie breaking. We had these two actions that had basically, as we run this algorithm for longer and longer, exactly the same cost in hindsight. Like they differed only in a tiny amount. And yet we were sort of swinging back and forth between these actions. You might sort of think that if two actions are basically equivalent, we should sort of randomize uniformly between them. We shouldn't select one of them preferentially over the other. And so rather than follow the leader, what we're going to analyze is an algorithm called follow the perturbed leader, which is going to keep track of what these cumulative costs were in hindsight, but then kind of noise them up, like add stochastic perturbations to them, and optimize not for the exact losses, but for the perturbed losses, for the noisy losses. And the intuition is that the noise that we add will sort of paper over small differences between actions. Okay? So the algorithm's almost the same. Every day we're going to compute the cumulative cost vector in hindsight. And then we're going to sample some noise. In particular, the noise vector at day t will be a vector such that each entry is selected uniformly at random between 0 and 1 over epsilon for some epsilon that we're going to set later. Okay, so we're selecting a d-dimensional vector where the distribution on each coordinate is just the uniform distribution between 0 and 1 over epsilon. And what we're going to optimize for is not the action that minimizes its inner product with the cumulative cost vector, but rather the action that minimizes its inner product with the cumulative cost vector after we've perturbed it with noise. Okay, so almost the same algorithm. Okay, I only had to like make 2 local changes here. Okay, and so yeah, like the intuition, right? And so let's just maybe like think about this for a second, because there's going to be a trade-off here in how we set epsilon that's going to come up in the analysis. The intuition is that like if the costs are sort of oscillating in this way, we want to be basically equally likely to pick each of the actions. So we want like the noise that we're adding to be big enough to sort of cover over very small differences. The noise will better cover over small differences. The larger the noise is, the smaller epsilon is. Of course, we also want to be like doing something related to the sequence of costs we've seen. We don't want to be playing purely random actions. And so as we scale up the noise, although it will make the algorithm less sensitive to small, maybe insignificant outliers, it will in general make the algorithm sort of more random and less sensitive to anything it's seen. And so that can't be a good idea, in the limits either. So there's going to be some trade-off to manage here. Yeah. The way we're analyzing it, epsilon is going to be fixed. We're going to set it in some way related to the time horizon. But just like these questions came up last time, if you don't know what the time horizon is, then you can sort of set epsilon dynamically and get the same kinds of bounds.
But then couldn't you also
No, that's what we're gonna prove regret bounds for this algorithm. Yeah, but like somehow if
it's like her one 0, 2, then 4, 0, then 0, 8, then 16, 0, and 0, 32, and then they keep on. So your noise never is always small.
Oh, but the adversary can only do that for like logarithmically many rounds. So like.
Oh,
yes. Oh yeah, that's right. So like obviously there's some relationship between the scale of the noise and the scale of the costs. Like if the costs are either 0 or 1,000,000, then adding noise, on human scales won't do anything. Yeah. So all of this is, really we're gonna, the final bounds will have a term that sort of depends on the scale of the costs. Or if you want, like when we analyze, same thing happens with multiplicative weights, like when we analyze things, we imagine the scale of the costs was like between 0 and 1 and proved some bound. If you scale up the costs, you can also get a bound, but they're correspondingly scaled up by the magnitude of the cost. Same idea here. Good. Okay. Other questions? Okay. Okay. So actually, yeah. So let's write down what's the theorem we're going to prove, and that'll make all of these dependencies transparent. Okay. So the expected cost, or sorry, the expected regret of follow the perturbed leader, FTPL, to each action A in the action space is bounded as follows. If I look at the sum of the difference between the costs the algorithm experiences playing a different action at each round compared to the benchmark cost of just playing a fixed action at each round. Okay, but we're gonna give this bound simultaneously for every fixed action, so it's the best fixed action in hindsight. This is going to be at most A over epsilon plus 2 CRT epsilon, which if we choose these parameters optimally, and I haven't told you what these letters mean yet, but patience. If we choose these parameters, if we choose epsilon to trade off optimally against these two terms, is less than the square root of 8 CART. Okay, now what are these letters? Well, it depends basically on the scale of the problem. So A is related to the diameter of the action space as, you know, as vectors, like how big are the vectors representing these actions. So A is the maximum over any pair of actions A and A prime in the action space of the L1 distance as vectors between A and A prime. Okay, so if we think of the experts problem, where the vectors are just the standard basis vectors, the indicator vectors for each of K, for each of D actions, this would be just 2. Okay, but more generally, for like the online shortest paths problem, would be related to like the length of the paths. C is the maximum L1 norm of the cost vectors. This is related to the question of like, would this still work if we just multiplied all the cost vectors by 1,000,000? Wouldn't that drown out the noise? Well, yeah, it'll make our, you know, regret bound correspondingly worse. The regret bound naturally has to depend on the scale of the costs, and it does. And R is the maximum magnitude of the cost that the algorithm can experience. It's the maximum over pairs of actions chosen by the algorithm and cost vectors chosen by the adversary of the magnitude of the inner product between the action and the cost vectors, the maximum magnitude of the cost experienced by the algorithm. Okay, so for like the experts problem, A would be a constant, because the actions are just like standard basis vectors. C would equal the dimension of the space, because you could have costs between 0 and 1 for each action. And R would be 1, because if you're choosing a distribution over actions, and each action has cost between 0 and 1, the maximum cost you can experience is 1. Okay, but more generally, these could be other numbers. These are the dependencies we're going to get. Okay, so does the sort of theorem make sense? But like basically what you should look at is, you know, the action space, the cost space, these are like fixed things. Okay, so whatever these things are, they're constants. We're getting regret bound that just like multiplicative weights is going to scale with the square root of t. It's going to scale sublinearly with time. So our average regret is going to go to 0 at a rate of 1 over square root of t. And we don't have any dependence on the size of the action space. Like these are combinatorial d-dimensional action spaces that could be, well, of course, they could be continuously large, but like they could be discrete sets that have size on the order of 2 to the d, like they do in the online shortest paths problem. We don't have an explicit dependence on that. Okay. And the running time, like the algorithm is extremely simple. We're just sort of maintaining these d-dimensional vectors. So everything's sort of, you know, running time like linear in d. All we're doing is at every round, we're making a call to this like offline optimization oracle. So like the running time is dominated by like how quickly you can solve these problems in the batch setting. Yeah. Well, it's a good thing it's not the number of actions, because that's going to be like exponentially large. So you know, lucky thing. We'll see how this comes up in the analysis. But you know, the intuition basically is going to be that yeah, we're going to need the noise somehow to like smooth out, you know, small differences that are sort of related to the vector valued representation of these actions. Okay. Good. So yeah, so this is the thing we want to prove. questions, but before we do it, yeah, it's possible in any case that the analysis goes over to next class. So like, before we like jump into it, are there questions about what we're proving before we prove it? So like, this is going to be an algorithm that can operate in sort of a combinatorially large space, exponentially many actions. The only thing we're sort of assuming structurally is that the payoff has this low dimensional, that somehow our interaction can be embedded in this low dimensional linear world where the payoff has this linear, d-dimensional linear structure. Okay. We're going to get sort of good regret bounds that scale, with like root t. And the computational complexity of this algorithm is going to be the same, basically, as the computational complexity of solving whatever our optimization problem is in the batch setting, because the algorithm is just, a pretty direct reduction to solving these like batch optimization problems. Yeah. Mm-hmm.
But a question after we go all about another around the top of like all of the
So for online shortest paths, there is. So for online shortest paths, there's a way to solve the problem where, you think hard about the combinatorial structure of paths, and you basically come up with a, implicit way to represent all of the weights on all of the paths. In full generality, as online linear optimization, I'm not aware of such an approach. So like, just to, like maybe another view of like what's going on here, like multiplicative weights, what it's doing is it is explicitly representing as a vector with dimension equal to the number of actions, the distribution it wants to sample from. And then it is sampling from that distribution, having written it down. This algorithm is skipping the step in which it explicitly represents the distribution. There's no explicit representation of the distribution. What we're giving here is a sampling algorithm. It samples from some distribution over actions. That is implicitly the distribution being played here, but there's no explicit representation. That could be a complicated distribution. Like if you ask me, what is the probability you play this particular path? I don't have a clean way of giving you that answer. I just have a way to sample from that distribution. What we're giving is a sampling algorithm for a distribution that is implicitly represented. Okay, so that's where the savings are coming from, like the avoiding explicitly representing this distribution. Yeah. Or it's a very big set is the.
One way in which it is interesting is to take with they have like a nice put a net over it.
Yeah, I guess the problem is that's gonna, like it's a d-dimensional space. So a net, like a discrete net over a d-dimensional space will have size exponential in d, right? Even like this is like the polytope of all paths in a graph. The convex hull of the vertices are like the paths in the graph. So it's a polytope that has exponentially many vertices. Paths have nice structure, but not everything does. Does that make sense? Okay. Okay. So the way we're gonna like analyze this algorithm is basically through a series of thought experiments. We're gonna think about what would happen if we ran various impossible algorithms that we cannot run because we don't have the information to run them, that are nevertheless like kind of similar to this algorithm. There's gonna be a chain of 3 algorithms we analyze, the first 2 of which are like impossible to run, but have really good regret bounds. The last of which is this algorithm. And what we're gonna argue is that all of these algorithms must have similar regret bounds. And so because the impossible algorithms have really good regret bounds, this algorithm must have kind of good regret bounds as well. Okay, that's going to be like the structure of the argument. Yeah.
So if it's like A is 0 and 1 first thing, then is that just going to be digit B?
A and D, where are we?
So in your
If A, like if the action space is all possible vectors where every coordinate can be between 0 and 1,
yeah, I guess.
then this would be like, yeah, D. That's right. So basically, like any of these things could be as large as D. Some of them will be smaller in structured settings, like if the vectors are sparse. Okay. Okay, so let's see. Let me erase the theorem because I'm not sure we're going to get to the end of the proof today. So maybe we don't, for the moment, need to remember exactly what it is we're proving. Okay, so like let's suppose we're going to get to one of these impossible algorithms. Let's suppose that we had the ability to see into the future, but like only a little bit into the future. Like it's a kind of a shitty ability. I can only see like a little bit into the future. So okay, so let's suppose I have the ability to see tomorrow's cost vector. So if I could do that, okay, there's an obvious way I could cheat. You know, I could just play the thing that is, you know, that minimizes cost for tomorrow's cost vector. But then it would sort of be like very obvious to everybody in the world that I was cheating, right? Like it's like every day I need to bet on the coin flip, it's going to be like heads or tails. If every day I get it exactly right, you probably figure out that like something funny is going on. So maybe I want to use this ability to cheat, but in like a less obvious way. Okay, so what I'm going to do is I'm not going to, you know, I know tomorrow's cost vector. What I'm going to do is I'm not going to optimize for tomorrow's cost vector. That would be sort of too strong a thing to do. What I'm going to do is I'm just going to run follow the perturbed leader, but like one time step in the future. Like I'm going to run follow the perturbed leader, but like, you know, the thing that followed the perturbed leader would have done tomorrow. Okay, so I'm cheating only a little bit. Like I'm running with the benefit of one step foresight, a bad algorithm. But I'm running it in a way I can't really run it. So I'm doing it with like one step looking. Okay, so let's call this thing B the, and let's say actually, you know, like follow the perturbed leader. We want to show actually that's a good algorithm. The thing I'm going to run is with one step foresight a bad algorithm. So I'm going to do it without the perturbations. Okay, so we're gonna run with one step look ahead. This thing that we showed was a bad algorithm. Okay, so let's call this follow the leader. What'd you say? Oh yeah, let's call it something else because that would be really confusing if like this was called the same thing. Let's call this be the leader. Be the leader. Okay, and what is it? At every day t, what I'm going to do is I'm going to play the action, I'll call it a hat of t to like distinguish it from what follow the leader is going to do because it's got like a hat on top of it. The action that minimizes amongst all actions the inner product of A and C less than t plus 1, where C less than t plus 1 is just the sum over all of the rounds up through and including today of the cost at that round. So this is what follow the leader would play tomorrow. Okay, follow the leader today sums up only through yesterday, because I don't know what today's cost is. Be the leader sums up from round 1 all the way through and including today. That's the part where it's cheating. It's like not cheating very well. Like if I knew what today's cost would be, I should just optimize for that. But that's not what be the leader is going to do. It's going to optimize for the cumulative cost from days 1 through t. So it's just the thing that follow the leader would do, except I'm doing the thing follow the leader would do 1 day earlier than follow the leader would do it. Okay, let's be the leader. Yeah. Oh, sorry, this is just my like terrible handwriting. This is the superscript says less than t plus 1. This is to communicate to you clearly and concisely that what we are doing is we are summing up over all of the days that are less than t plus 1. Yeah. No, it's less than or equal to t, which is the same as less than t plus 1. Okay, good question. Yeah. Good. Other questions like that? Okay. Okay, so like we can't like it's not obvious this is a good algorithm. It's just running a bad algorithm, but like 1 step shifted into the future. But like also it's not like it's possibly a bad algorithm, but it's also one we can't run because we don't know 1 step into the future. Okay. Okay, but like nevertheless, the claim is going to be that it's not a bad algorithm. This is actually a good algorithm. This algorithm is always guaranteed to have 0 regret or possibly negative regret to the best action in hindsight, but never positive regret. Okay. Okay. So like the lemma is that be the leader has non-positive regret to every action in A. Okay, so in math, if we sum up the cumulative cost that B the leader has at every day, that's just the inner product with the action it picks and the cost vector, this is guaranteed to be like less than the cumulative cost of every other action. Okay, there's no like plus root t here, like it's not like we get a root t regret bound, like we never have any regrets at all if we play be the leader. Okay, so it's like really good as measured by this regret benchmark. It's not as good as if it's optimized for tomorrow's cost. Like it's not going to guess the outcome of the coin flip every day, but it won't do any worse than always guessing heads or always guessing tails. Okay, does that make sense? That's the claim. And of course, we can't run it. Is like the one caveat because it involves looking into the future and then making especially bad use of that information, but is going to be interesting as part of our analysis. Okay. And so we're going to prove this by induction on T. We're going to sort of say, okay, like it's true for T equals 1. And if it's true for T equals K, it's also true for T equals K plus 1. And since there's only countably many integers, it's true for all T. Okay. So like the base case is immediate. The base case is T equals 1. And like by definition, like what is A1? Well, this is just the action that minimizes the inner product with C1, right? Like, at day one step look ahead really does just mean optimizing for today's cost because there hasn't been any history so far. And so, like the thing we play at day one is the thing that minimizes cost for the first day. And so the base case is established. This is, if we only run this for one round, like we really are, like at round one, this really does amount to just looking one day into the future, seeing if the outcome is heads or tails and guessing that. So at day one, there's no way to beat this algorithm. Okay, so the only thing we need to worry about is that we're using this information suboptimally at days, 2 through t. Okay, that makes sense. Okay, so now, like, inductively, we're going to assume the claim is true for, t less than or equal to k. And now we need to prove that the claim holds true for day k plus 1. Okay, so let's look at the cumulative cost of the algorithm at day k plus 1. This is just the sum over all of the rounds of the algorithm from round 1 to k plus 1 of the inner product between the action played by be the leader and the cost vector on that day. And I can, right, we're doing an induction on k, so maybe it's going to be useful to like break this sum from days 1 through k plus 1 into like two parts, the sum from days 1 through k about which I can assume something, and like the one extra day. Okay, so let's do that. Right, so that I can sort of write this as first the sum from days 1 through k of the expected cost of the algorithm plus, like this one extra term that didn't get included in this sum, the cost of the algorithm at day k plus 1. Okay. Now, this is the cumulative cost of the algorithm from day 1 through k. So this is the thing I get to apply the inductive assumption to. And what was the inductive assumption? That that my regret was non-positive to every fixed action. Okay, so this is bigger than the accumulated cost of any other fixed action. Okay. In particular, it's bigger than the accumulated cost of action a hat k plus 1. It's bigger than the accumulated cost of the action that be the leader chose to play at day k plus 1, because it's got cost less than every action. Okay. So like this is at most applying the inductive hypothesis, the sum over all of the days of a hat k plus 1 ct plus the inner product of a hat k plus 1 c k plus 1. Okay, all I'm doing is I'm saying, this dynamically chosen action does no worse than any fixed action. The fixed action I'm going to choose to compare to is like the fixed action that the algorithm happens to decide to play at day k plus 1. Okay. But this, of course, these are inner products. They're linear. I can, the thing in the left of the inner product is fixed. It's just this fixed action a k plus 1. I can, instead of summing over the inner products, I can bring the sum inside of the inner product. So this is just the inner product of a hat k plus 1, the fixed action that is unchanging throughout this whole interaction, and the sum from days 1 through k plus 1 of the cost on those days. right? It's just, inner products are linear. I can bring the sum inside. Okay, but what's the last line of the proof? How do I know that this is less than the accumulated cost of any other fixed action A? Yeah, like what is A hat K plus 1? A hat K plus 1 is defined to be the action that minimizes this inner product. That is how we defined it. Okay, so that is A hat K plus 1 amongst all actions is the minimizer of this inner product. And so, like just because minimizers are like small compared to everything else in the set you're minimizing over, this is at most the inner product of A with the accumulated cost, which is what we were trying to prove. Okay, is that clear? Like somehow follow the leader, although it's not doing something reasonable as we saw if you run it in the way you're able to. If you could run it sort of just shifted one step into the future, which is what be the leader is doing, it would sort of be doing a sensible thing, and it would never have regret. Okay. Questions about that statement? Right, let's see, how many more lemmas can we squeeze out? Maybe one more. Okay. So remember, like, ultimately we want to analyze follow the perturbed leader. We're sort of taking a journey there. We started with sort of be the leader, which differs from follow the perturbed leader in two ways. One is there's no perturbations, and the other is it can see one step into the future. The ability to see one step into the future was really good. It gave us like zero regret. So now let's think about be the perturbed leader. Suppose we can see one step into the future, but now I'm going to like add noise as well. Okay. The thing I want to show is that I'm not going to do better, like I already have zero regret. The thing I want to show is I'm not going to do too much worse. Like adding noise won't make things too much worse. Okay, I'm still like looking into the future. That's cheating. I'm doing too good. I'm going to try to make myself do worse by adding noise. Okay. So be the perturbed leader. It's just going to be the same thing as follow the perturbed leader, but with one step look ahead. Okay. Okay, so let's say it's just, again, follow the perturbed leader, but playing one step into the future. So I look one step into the future, and I optimize not for the cumulative cost vector, but for the noisy cumulative cost vector. Okay, so we're getting closer to follow the perturbed leader. Now there's noise again. Now we're sort of looking at what happens if we play the actual algorithm we want to analyze, just sort of shifted one round into the future. Okay. So the lemma is going to be that B, the perturbed leader, has regret to each action A. That's not too big. If I look at the difference between the cost at each round of B the perturbed leader and the cost of any fixed action well, if I were playing B the leader, this would be 0. It's not going to be 0, but it's going to be at most A over epsilon, where remember, A is the diameter of the action space. Okay. So at least if epsilon isn't too small, if I'm not adding too much noise, I won't have too much regret. Since we only have a minute left, maybe rather than jumping into the proof of this, because there's still a couple more lemmas to come, let me give you intuition for what's happening in this analysis, and you know, depending how we feel, we can finish the proofs next time. So, okay, so we just analyzed B the leader. Does great, but we can't implement it. Now we're explicitly making that algorithm worse. We're adding noise. And it sort of makes sense that, first of all, why do we want to do that? Well, the reason we want to do that is because we can't look one step into the future. Okay, we have to run follow the perturbed leader. And as we've seen, there's a very big difference between follow the leader and be the leader. This sort of, the difference between running follow the leader as you can actually run it and running it shifted one step into the future is that in this example where the costs are alternating, every day follow the leader plays exactly the wrong action, whereas be the leader plays exactly the right action. Okay, so it's like, those are pretty different algorithms, even though the difference is only one step into the future. The reason we want to add noise is because the algorithms are not going to be very different if we add noise. Right? What's the difference between follow the leader and be the leader? It's that we're optimizing for a cost vector, a cumulative cost vector that it sums over one additional day for be the leader. If the noise we're adding is sufficiently large that it sort of swamps out the contribution of a single day, then in distribution, these two algorithms are going to be doing something very similar to one another, right? Like what noise does is it sort of turns the distance between vectors in Euclidean distance, into distance in distribution, right? If I add noise to two vectors that are close, in like parameter space, the distribution over noisy vectors will be close in distribution, which means that if be the perturbed leader is a good algorithm, it gets low regret, and it's very close in distribution, it's doing something very similar every day to follow the perturbed leader, then follow the perturbed leader must be also a very good algorithm because we can't really distinguish between these two algorithms reliably by any metric, including the regret of the algorithm. Okay, so like what we need to show is that adding the noise doesn't hurt be the perturbed leader too much, that it's still a pretty good algorithm. And then the next thing to show is that, if we add not too much noise, be the perturbed leader is a pretty good algorithm. If we add sufficiently much noise, be the perturbed leader is very close in distribution to follow the perturbed leader and therefore has similar regret bounds. And if we balance out these two things, it'll be a good algorithm that's similar to follow the perturbed leader, which will mean follow the perturbed leader has low regret as well. Okay, those are the remaining steps that maybe we'll work out next time. Administratively, I already posted in the Slack that a week from today, next Monday, I'm scheduled to give a talk here at Penn, but directly up against this class. So no class a week from today. The thing I did not mention sheepishly is that there's also no class Wednesday. I'm canceling 2 classes in a row. Sorry, bad scheduling. I'm going to be in Berkeley giving a talk, or flying to give a talk this Wednesday. So embarrassingly, there are like 2 classes in a row in which I am shirking my duties. I'm not going to be here lecturing either Wednesday or the following Monday. In penance for the Monday, though, you can sign up to listen to all these interesting talks. But in penance for this, I'm gonna in this interregnum upload to the website, maybe like a list of a bunch of papers that sort of are adjacent to the things we're thinking about in this class, so that you can take a look at that and start thinking about what you might be interested in for your final project. So, and you can also look at the notes that are linked on the Slack to sort of get a trajectory for where we're going to be going in this class. So there's a whole constellation of interesting stuff adjacent to what we're talking about. A good thing to do in the week of no class is to start using these resources and thinking about what you might want for your project. And then I will see you back in this room a week from Wednesday. Okay, I'll post this on the Slack as well.